So yeah, so we will start with the bias in AI. So this will be a very short lecture. Today, and then we will conclude. So the thing is that we have discussed about explainability, and we have touched a little on bias. I mean, how it can help in discovering the bias and then mitigate it. But we'll go into much more detail of it. At least that is possible for one lecture. So we'll first define what is bias and so on, and how can it affect, what are the sources of it, and then later we'll in detail discuss about one work in computer vision which actually mitigates a type of bias in image captioning models. Okay. So machine learning models are, increasingly used to inform high-stake decisions about people. But for all their enormous potential, ML-powered systems have a very dark side. So their decisions are as good as the data, actually. And this makes these ML algorithms very vulnerable to bias. And that is already present in the data. I mean, it's not only that it can reflect the bias, it can actually in many cases exaggerate the bias. So we'll see what we mean by this in image caption. So now ML systems are more and more used in making hiring decisions, making say lending loans decisions, even finding future criminals to help the administration to decide on say bail or parole, etc. So there are lots of examples of algorithms being biased that came up in media actually recent times. So some of them are actually listed here. From women being say less likely to be shown high-paying jobs in job advertisements, say racial bias in photo apps, to gender bias in machine translation. We'll have some examples of that. Here briefly we will discuss about one or two case studies, and then we will jump into one recent work on how to mitigate gender bias in image captioning system. So this definition of bias, I have taken it from one very old paper, Bias in Computer Systems by Friedman. So it says this computer systems that systematically and unfairly discriminate against certain individuals or groups of individuals in favor of others. So example again from the same paper, for an automated say credit advisor, automated credit lending system, system denying credits to individuals with consistently poor payment record is not a bias system, because that is reasonable. I mean, any bank would want that that okay, it should not give or lend money to someone who has poor payment records. But if you are systematically denying to individuals with ethnic surnames, it's unfair discrimination, and that is not because this criterion is not relevant to assess the credit rating. So there are two important things. These are actually told in italics here. So systematically and unfairly discriminate. So one thing is that unfair discrimination alone does not give rise to bias unless it occurs systematically. So imagine again that credit applicant having ethnic surname, but if a random glitch in the system, say mistakenly copies some credit information from another person, and that lowers the applicant's rating of getting a loan, then this applicant experiences unfair discrimination resulting from this random glitch. It's not occurring systematically. That applicant could have been anybody. So it's not an example of a bias. But system, again, I mean, the second extreme of it is that system discrimination or systematic discrimination does not establish bias unless it is joined with an unfair outcome. If it is not unfair, if it is a systematic discrimination, it can be an error. So let's consider a car tracking system. Due to impression in calculation, if the car's position gets wrong, then it's an error, but doesn't bring about an unfair outcome. So this is some subtlety about that definition that we have used in bias. And some cause of this unfairness or bias. There are these three main causes that has been listed in this very good paper by Aaron Roth. So the frontiers of fairness in machine learning in 2018. So I can ask you guys to basically go through it. It's a very good paper, and there are many good discussions on unfairness, where from it comes, and how to mitigate, how to evaluate, and so on. So I have just taken these sources of unfairness from that paper. So one is bias encoded in the data. So there are already biases in the data. We have social prejudices and so on. Sometimes the some data is not easily available. That makes the data biased towards the data that is easily available. So, for example, I mean, this is a line that is taken from that paper. So, ML techniques are designed to feed data and so will naturally replicate any bias already present in that. And there is actually no reason to expect them to remove the existing bias. Though early AI researchers thought that maybe we are biased as human, but since this is a kind of non-human thing, it might actually help us to remove bias. But actually, it tries to learn from the data at hand. So if we expect that it will remove the existing bias, naturally it is not, I mean, there is no reason to expect that. Another thing is minimizing average error fits majority population. So ML algorithm cannot simultaneously fit to all populations optimally. So it will fit to the majority population. So it will be anyway biased to the majority population, what is coming to majority. So the fit to majority population is more important to overall error than to fit to minority population. So even if that means that you will discriminate against the minority population to reduce the error in training, it will fit to the majority population, because by virtue of the number, it dominates the majority population. And the need to explore. So we don't really explore much in traditional supervised algorithms. So that comes in RL, and there are, I mean, reinforcement learning, and there are ways to do that. But if we only observe whether an inmate will recidivate if we release him. So recidivism is an application where basically it tries to predict if a dependent should receive a bail, and that is one algorithm compass, it is called, that is used in US, and that actually caused a star by this ProPublica article, which showed that it is actually biased against some ethnic group. So if we only observe whether an inmate will recidivate if we release him. So we only observe the efficacy of a drug on patients to whom it is assigned. So this is like what we have observed, we can only model. So, but learning theory tells us that in order to effectively learn in such scenarios, we need to explore. That is, sometimes we need to take actions we believe to be suboptimal in order to gather more data. Because otherwise, where will we get data if, say, for we want to see that the drug, what will be the effect of the drug if it is not assigned, and something like that. If we don't release him, what will happen? So where will we get it? So that may be suboptimal to do, but we have to do it for getting more balance towards these minority cases, or that doesn't occur much. So then only they will cover all scenarios, which will in turn help to reduce bias. So these are only just very brief reasons why there may be unfairnesses. There are maybe many other reasons, but again, I mean, this is taken from this paper. I just urge you to go through this paper if possible. So this is one example. So this is one system, this compass. I mean, I briefly flashed this slide. So this system actually predicts if a defendant should receive a bail, and this actually helps to help the justice to decide whether they should receive a bail or parole, etc. But we see that this ProPublica article actually saw that revealed that it is more likely to wrongly deny a black person bail. So wrongly labeled as high risk, these black persons, it is almost 45%, and this is like 23% for the white. While wrongly labeled as low risk for the whites, who have been basically say allowed a bail, they actually did this. I mean, 47.7% of white persons actually, of such persons who received bail, committed again crime. But out of the black persons who received bail, 28% actually only committed. So this is actually discriminating against the black person, and it depends on the data. Probably the data that they had trained the algorithm on was not actually covering all scenarios. So this actually caused a pretty much star in the fairness community. Again, this example of AI unfairness, this one example is for word embedding on natural NLP application. So we have seen word to vec example. So it is just again a brush up of it. So word to vec or any word embedding is just a mathematical representation of the word. So representation each word with a high dimensional vector. So we can use this to find vector arithmetic, find say analogies like if Paris is to France, then what is London? Then this thing like if man is to king, then what will be woman to? So the good news is that word embeddings learn so well. The bad news is that sometimes too well. So our chatbot should be less biased than we are. And all these analyses are there in this paper from Bolumpas et al. Man is to computer programmer as woman is to homemaker. Debiasing word embeddings in NIPS 2016. So there is one, I think, slide which I have taken from this paper. I mean, this is some analysis. I mean, they have some ways to mitigate the bias, but I will not go into this. Instead, I will focus on a computer vision algorithm from next slide. But this is just to good to know about this unfairness about this word embedding. So this left list, it tells what? It lists all the occupations that are closest to C and to he. So this one is closest to, I mean, this list is closest to C and this list is closest to he. And it has been, this word embedding has been trained on something called W2V news. I think, yeah, here. It is a corpus of Google News text consisting of, I think, 3 million English words. And the word embedding dimension is 300 dimension. So here, it's just three dimensions it was shown here. So it is 300 dimension vector. So on that, it has been found that these are the words which are very close to a female gendered word. For example, nurse or this hairdresser, nanny, etc. Housekeeper, but he is this captain, philosopher, magician, financier. So these are very much stereotyped. Another is these words, the right hand side. These again come from those analogy type thing that okay, if man is king, then what is woman up to? These kind of analogies, and we see that these are automatically generated. I mean, examples of automatically generated analogies for the pair C he. So, for example, this first analogy, it is telling that if C is to swing, then what is he up? In this word embedding this W2B news corpus. These right bottom are some examples which are appropriate pairs, and these are basically the stereotype pairs that has been found in this. So next I will go into this very good paper. I like this paper very much. I think this is the very first work on mitigating bias on captioning models. But before I go into this, I'll just stop for a little for if you have any questions. So you can unmute and ask. Okay, if you don't have any questions, I will then go ahead. So this is Omen also snowboard, overcoming bias in captioning models, and it was an ECCB 2018 paper. Okay, so let us see what are kind of the effects of bias in image captioning models. It can affect in many different ways. So we have seen this example when we tried to show why we need explainability, but again, it is always better to revisit. So this is saying that captioning models may make errors due to bias. We have seen that when we see the importance map or the saliency map for the word man that is being generated here in the caption, it is first of all, it is generating a man sitting at a desk with a laptop computer, some traditional captioning model. So for this word man, when we generate the explanations, we see that the evidence is coming from this computer. So it is not actually focusing on the person who is in front of the computer. So this is again coming from this dataset bias, the social prejudice, as I have told earlier also, that the dataset actually contains lots of images of computers which has male in a person, a man in front of that. So it is again very much similar to our real life examples or scenarios. Many of the images, many of the computer related jobs we associated mostly with men. So it's sometimes called, I mean, the data or the algorithm, machine learning algorithms are just social mirror. So whatever we have in our society, it just gets reflected there. So it is a very good example of this. Again, the captioning models may base correct prediction on wrong evidence. So the earlier one was itself wrong. The correct prediction was wrong. But here it is, the caption is telling that a man holding a tennis racket on a tennis court. But when it is generating the word man, it is actually basing the prediction on wrong evidence. It is basing on the racket. So it is right for the wrong reason. So that's also an effect of bias in captioning model. Because maybe that the image, the data set has lots of images with a tennis player who is a person, who is a man, not woman. Then again, captioning models hallucinate objects based on the context. So there are lots of maybe this kind of images where you have people or person who are talking on a cell phone, but they sit on a bench, so, or somewhere, say couch or cushion or something. So it's just hallucinating that a woman talking on a cell phone while sitting on a bench. So there is no bench here, at least that can be seen from the image. So that is another effect of bias. So what's worse is that performance metrics fail to capture this also. So this is one slide that I mentioned earlier, that the bias can be actually exaggerated in captioning models. So in traditional models, the baseline models means just a traditional captioning model, what we have also discussed earlier, that it just encodes says, the image as CNN features, and it feeds into a recurrent neural network or LSTM, any type of recurrent architecture with a start token, and then it generates the words until an end token is generated. So if the ground truth captions in say this say data set has gender neutral words of 22.4%, women words with 28.8%, and man as 48.8%. If you are actually predicting on these captions using this baseline or a typical or traditional captioner, it will actually exaggerate the bias. You see the man percentage have increased from 48.8 to 57, and women has basically reduced. So it actually learns from the bias data, and it can exaggerate the already present bias. It is already biased. It is 50. Basically, the man word is almost 50%, 49%, but it is here. It is more than 50%. It's 57%. So that is again, this observation came from this paper. Okay, so now this paper actually uses some techniques to base the right gender word. I mean, predict the gender word basing on the right or appropriate evidence. So if you apply the proposed approach and then use an explanation model on the predicted gender word, you will see that for the same image, where traditional methods gave this man predicted word, I mean the predicted word the predicted gender word based on this racket, here it is actually basing on the person. So let us see how that is achieved in this paper. So here the intuition so behind this is that it actually applies one model called equalizer. So it equalizes and it's an existing vision and language model. It's just builds on that and consists of two losses. So appearance confusion loss. So the intuition behind the appearance confusion loss, this first one, is that given an image in which evidence of gender is absent, somehow we'll see how that the authors have made if possible, how the gender information is made absent. The description models would be unable to accurately predict a gendered one. However, it is not enough to confuse the model when the gender is absent. It must also encourage the model to consider the gender evidence when that is present. So that is where this confident loss is coming. It encourages the model to be confident when the gender evidence is present. And what is appearance confusion loss? It encourages the model to be confused when the gender evidence is occluded or not there. The confidence loss does this gender evidence being sorry. Okay, so unfortunately PowerPoint crashed. So again, I'll just briefly tell about this slide again. So this has two losses we have seen. So one is appearance confusion loss, which encourages the model to be confused when the gender evidence is occluded, and one is confident loss, encourages the model to be confident when the gender evidence is present. So it has two components of the loss. And I like this line from the paper, very good. So it is these complementary losses, these are two complementary losses, when the gender evidence is occluded and when the gender evidence is present. So when, I mean, rightly it is saying that when the gender evidence is occluded, it will be confused. So it should not produce any gender words. And when it is seeing any gender evidence, only then it will produce the gender words. So these complementary losses allow the equalizer model to encourage models to be cautious in the absence of gender information and discriminative in its presence. So which actually aptly sums this paper, I'd say, if I have to sum the paper in one line. So let's see what it does in a little more detail. So before going into the detail, this is the baseline description framework. That is, what is the baseline method? So we have seen it right earlier. What is the baseline method for image captioning? So it says that to generate a description, it says that high-level image features are first extracted from some inception V3 model. I mean, it can be any CNN. The image features are then used to initialize the LSTM hidden state. That encoded features will go there. To begin the sentence generation, a start token is input as the first input to the LSTM. And for each subsequent time step during training, the ground truth word W2 is input to the LSTM. And at each time, the previously predicted word W3 minus 1 is input into the LSTM at each time. So generation concludes when an end of sequence token is generated. And the loss is, of course, the standard cross entropy loss. So this is log of probability of the generated word given all the words generated till that time and the image. I think T is the length of the sentence and N is the batch size. So why did I include these sentences from the paper? Is that I found this is a very good summary of a image captioning model. If you ever forget what an image captioning model does, if you just brush up these lines, it will be, very, very crisply clear. So that's why, though it's a repetition, I have just included it. Now, this says that the approach, the overview of the approach. So the idea behind the equalizer model is very simple. So we have this original image I, this one. When you use the original image, the generated word here, the man, should be predicted. Then a new version of the image I prime is actually generated where the person's image is masked out. See, if you can see it good there, that this person's image is masked out. So how is it masked out? This or I prime is generated. It is element-wise multiplication, or technically called Hadamard product, with a mask where this of the original image, where the M is the mask, where the values are 1 for pixels which should not contribute to a gender decision, and 0 for pixels which are appropriate to consider when determining gender. So if you are multiplying this is the mask, all these are 0 here. So basically you are not giving any information from whatever is there under this mask. So you are basically occluding this image, and the mask actually has 0 for all the portion of the image where there is gender evidence, and 1 for everything. So you are passing everything that is under the mask of value 1, and you are passing actually nothing, where the mask value is 0. So this slide shows again the overview of the approach, the losses that are basically used. So details are coming in the next slide. So it says that for both the images, that is I and I prime, the masked and unmasked, a standard cross entropy loss is there. So the standard cross entropy loss is this one, right? So the standard cross entropy loss, what it does is this is for every word. So this is coming from a man till every word, then in the end of sentence. Everything is coming to this caption correctness loss, and this is this caption correctness part. I mean the standard cross entropy loss. So now for the unmasked image, you want a loss. Let us go to this unmasked image. You want a loss which will confidently produce the gendered word, that is this man word. Only this man word is coming for this confident loss. So I mean this is the confident loss, and this is coming from only the gendered word, that is man here, not from any other gendered or non-gendered word in this caption. Yeah, this confident loss, the only contribution is from man, but this caption correctness loss, which is the standard cross entropy loss, is coming from all the words in the caption. Now, similarly for this masked image, the gender word will give rise to confusion, because there will, I mean, the model should not actually be predicting man or woman with high confidence here. So that means this confusion. The model should not be sure to produce any gendered word. And that is the appearance confusion loss part of it. So it is also concerned with the gendered word in the caption, only the gendered word. So whatever is the loss, we will come to the loss formulation, but whatever is the loss, it will be a function of only the gendered word. This appearance confusion loss for masked image and this confident loss for unmasked image, they will be a function of this gendered word. But the caption correctness loss, it is for coming from all the words. Okay. Now this should not be, I mean there should not be any confusion for the non-gendered word in this caption, even if the image is masked. So let's go into much more detail of these loss formulations. So let us first go into this appearance confusion loss. So for first, let us see what is this GW. I mean this GW and GM. So means this GW means a set of woman gendered words, and GM means a set of man gendered words. So he, him, then say man, etc. So these are the man gendered words. So let us see what this expression, the last one, tells in the slide. So the first term here, this one means that is the probability that the generated word, this WT tilde T, this is basically the generated word, and WT will see here, that is the ground truth word. But let's consider on or focus on this. Sorry. So the probability that the gendered word given the previous generated words or during training the previous ground truth words and image features, that is I prime, belong to set GW. So this GW is coming from this GW. So this is giving again the probability that the generated word given the previous words and the image features belong to set GW, this one. Similarly, the second term, that is this, means the probability that the generated word is a male gender word. Remember that this is the situation when the image is I prime, that is the person is masked up here. Then this C, this one, this is a difference between these two probabilities, a kind of absolute difference. So this C will be minimum, that is 0, when both these probabilities are same, because it is an absolute difference, the minimum value will be 0. And when will it be 0? When these two are same, the probabilities are same. That means no gender will have a preference over the other, right? Now the term just above it, now this is used here. So it is the appearance confusion loss, LAC. This actually tells to consider this loss given by this term C, we just described, if the generated word is a gender word. So this is the indicator function when it is saying that you consider this C when the ground truth word or the is coming from the gender word, then only you consider this. So this is the form of the appearance confusion loss. And what is the confident loss? So let's come to this part then. So this is for the masked image. Now this is for the unmasked image. So this confidence loss actually encourages the model to predict gender words correctly when gender evidence is present, that we have told earlier. So it has two terms. One is denoted by this FW and the other is FM. So FW is written here. We'll describe FW and then we'll see the FM will be very similar. So this FW and FM. Now what is FW? Let's see what is this. So it's the quotient between the probability of predicted word. So it's a quotient first of all. The probability of predicted word being male, this one, to that of being female, again given the previous words and the images. So we want this to be low, because any loss we want to be low if the ground truth word is a female. So this is given by here. So indicator tells that if the ground truth word is a female, then FW comes into picture. If the ground truth word is male, then FM will come into picture. And let us try to see the significance of FW and then we'll go to FM. So, but whatever is FW, it should be considered when the ground truth word is coming from woman. And what is FW? It is the quotient of two probabilities. What is whether, or it's a quotient of the probability that it is a male gendered word to the probability that is a female gendered word. So since it is considered when it is coming from, the ground truth is coming from a female gendered word, we want this to be high, right? The predicted probability of female word will be high. And if this is high, then only it is low. So we want the loss to be low. So this is a clever kind of use of quotient instead of just, we could have, or these people could have used a loss which will give more weight to a kind of gendered word. When it is predicting a gendered word out of all these captions, it could have just given more weight to these gendered words. But it has some disadvantages we will describe. They have actually compared with this as a baseline. But this is a very clever use of quotient. When the ground truth word is female, this you should expect as high. So this quotient will be low, then the loss will be low. Now I don't need to even describe what is FM. FM is just the opposite. So it is coming from male word. That is when the ground truth is a male word. So in that case, this quotient will be just the reverse. So you will have high probability for the male word. And then only this denominator will be high for FM. I have not written it here. And then only this will be low. So again, I think I'll stop after just one more slide, and if there is any confusion, I'll again try to answer. But let me just continue for the time. So one nice property of considering this quotient, as I said, it encourages the model to distinguish between gendered words without forcing the model to predict a gendered word. For example, if the model predicts a probability of 0.2 for men and say 0.5 for woman and 0.3 for a person on a woman image. So 0.2 for the word man, 0.5 for woman, and 0.3 for the word person for a woman image where there is a woman. The confidence loss will be low, right? Because it is 0.5 and this is 0.2. However, the model is still able to predict the gender neutral words like the person with relatively high probability, which has 0.3 probability, which is relatively high. So this is basically one of the advantages of the quotient, as I said, with some specific example. Now, I'll go into this kind of the last slide at least. I'll not go into much more details of kind of the quantitative metrics and so on, but this slide compares a qualitative result where you have a baseline, which is just this. So just a traditional captioning model. And the upweight is the one that I told earlier, that you just basically give more loss or more weight to the loss coming from the gendered words. You see that it is still producing similar word, that is a man. Here just on a leash, on a slope, but here the person walking a dog on a leash. Now, both of them, when it is generating this person or the gender word, man, it is actually focusing on the dog, because maybe that you have these images. It is not maybe, I mean, they have created these biased captioning data sets. If you go into this paper, you will see where you have, I mean, they have deliberately created this for experimentation. So it basically is when you give more weight to the loss coming from this gender word, and we see that this baseline also is not able to correct it, and it is also again still it is predicting or basing its evidence on this wrong concept. I mean, not on the person. So here, when this equalizer model is applied on the proposed approach that is applied on this image, it shows that it is actually generating this gender neutral word, which is person, and it is evident. I mean, the word is based on this evidence, the person evidence. So it is not actually basing on this dog. So this is kind of the advantage of this equalizer model. So I think I am done with this lecture, but I'll stop just to invite questions from you, maybe on this lecture and also on anything else. But first, ask if there is any question on this lecture. So is it then clear? I mean, how does these losses works and so on? This loss. I mean, this is only bit of maths that is there in the in this paper. Okay, thank you then.